Okay guys, so we're going to talk about the OSH6 for Math102. Particularly long OSH, a lot of words. But yeah, I'll try to make sense of this and let's get started on this. So what they're talking about in this one is differential equations is the main topic, and we're discussing about ectotherm temperature regulation. All we're going to be concerned in this one is that we have a differential equation right here that models temperature of any organism given various factors of the environment like Km, Ks, Kn, and T environment. All of these things are going to be constants. Km represents the metabolism heat constant, S represents the sun heat constant, Kn represents the Newton's law of cooling constant, T environment is the environment temperature. Okay, so they've given us all those things, and for the context here, we're fixed at 28 degrees Celsius for the environment temperature. And I'll just talk about the first part. The first part asking you to find the steady state for this differential equation. By the definition of the book, steady state of any differential equation is when that differential equation is equals to 0. So now in this case, we have an equation variable t and t here as well. So we're trying to isolate for the special t that makes this dt dt equals to 0. All you got to do is put this thing equals to 0. I call this TSS because that's the steady state time. So when you put it equals to 0, solve for that, you're going to get this value out here. Okay, pretty straightforward. So now we're going to start to talk about data fitting. Second part asks us to actually find a steady state data. So what they've given us data for various measurements in time for the temperature of an iguana's body. Okay, in two different cases, where the first case is with the sun, where the sun is actually shining on it. The other one is in the shade. So there's no effect of actually Ks happening in the situation. We're going to be focusing more towards the no sun case because that's where they wanted to talk about it. And it's easier to fit in the model, so we'll discuss that further. But yeah, before we do that, we have some data. So what they're telling us in the first, let's say 55 minutes, the temperature readings are always like decaying because when you're in the shade, your body's cooling down, and then your body temperature just becomes stable after some point. So that stable kind of data comes in the zone where you have time more than 60 minutes. So in the last hour of the measurement, the data is giving us somewhat relatively kind of like stable value, somewhere around 33-ish degrees. So what we'll try to do is we'll try to find a linear line with no intercept, okay? So no intercept line into that data. And by the methodology, that must be just the average. Okay, so what I did here is I took the average of the data given out to us. I did it in the Excel. I'll show you how to do that in part when we start actually 1D. But this is how we got the average value here for the time. So actually what happens is you gotta form the equation again. So when there's no sun here, your Ks will become equals to 0 because the S factor will have no contribution towards the differential equation. In this case, you have dm dt to be a very simple equation. I plugged in the T environment because why not? And then from this point, you just say by the best fit, what we figured out the stable steady state for this data is going to be 33.0384. I'm just keeping in extra units, extra decimals just in case. I'll show you exactly how I did it once I jump to the Excel part in 1D. So hold your horses for that time. And then because this is the data steady state, how about the steady state from the equation? If you try to do that from the equation, whatever this Km plus Can bracket 28 minus TD, actually T is going to be equals to 0 when you hit your steady state. So when you start to solve for the TSS, the steady state value, by equating this equals to 0, what you get is going to be Km over Can plus 28. So now the theoretical formula steady state needs to be this. The data steady state is that. So for our case of data that we're observing, we can figure out the ratio of Km over Can, which is this quantity, by plugging in the steady state data here. Okay. Once you do that, you get 5.0384. That is going to be the Km over Can ratio. All right, so now after that, we're going to talk about the case with the sun. So when you have the sun actually there, you can't make ks equals to 0. So we have the standard equation that we had in the beginning. I just plugged in the t environment there as 28. And now they're giving you the data for with the sun case as well. So we're going to do the same kind of analysis, find the average value of the data that's from t equals to 60 till t equals to 120 minutes. So in that zone, we found out the average in Excel from this. Again, I'll show you that once we go there. The average data is here. Now this theoretical steady state is what we found out above. The t steady state must be equals to that. Now, because of this, the data steady state is that, the theoretical steady state is this. We already know what km over kn is. We already know what t environment is. So we only have to figure out ks over kn. When we isolate for ks over kn, from this point, you can say it's TSS minus t environment minus km over kn. And we're plugging in all the values that you know. TSS is from the data. T environment comes from here. And then the km over kn is something that you just found out here. When you plug them all in, you get the ks over kn ratio to be this number. And that's about it for part B. Now in part C, what they want you to do is actually like follow the methodology that they're given out in the book to find the solution of this equation. So the solution, how it works is, all you do is you first of all start by actually assuming the whole differential equation that you had, like this whole thing right here, as some z, okay, some z value. That's also going to be a function of time. So when you do so, what you get is that this function, which is literally the z, is also equals to dt over dt. It's very hard to say, but yeah. So that's what z is. So keep that in mind. Now when you take a derivative of all of that, what happens here? When you take a derivative of this equation, that kn times t will just go to 0 because they're all constant. The only thing that you'll be left with taking a derivative of is going to be kn times negative t. And because they're both functions of time, that's the relationship you're going to get. So now this is a very standard equation where we're getting there. We know that dt is what we called as z here. So I can substitute for that. So my equation becomes a very standard decay equation. Okay, when you have the standard decay equation, in this case, you can directly jump up to the conclusion because you've been doing it in population models before as well. The solution to this equation is that some z must be equals to some initial z0 value e to the power negative kn times t. Okay, because this constant here is negative kn. So every time when you're trying to solve a differential equation, I think most of you guys just remember the standard form. But this one kind of comes in handy when you're actually solving it. The method goes like this. So I'm going to recap a bit. All you got to do is take this differential equation that you're given, make it equals to z, take a derivative of both the sides, and you'll always see the magical thing popping up back again. You'll substitute that z back in, and then you'll always end up with the standard equation here. And that equation, you can jump up to the solution right here because of basic knowledge with exponentials. All right, so now we have it in terms of z. We still have to figure out what exactly t is. So now we need to replace for z0. Z0 represents the initial z value. Well, the initial z value will be whenever the t was initial, right? So all you got to do is plug in t initial, which is t0, in that equation, and that becomes your initial z value. The actual z value is just nothing but the whole equation that you just substituted here, okay? This is the whole equation. So now from that, what you want to do is you want to plug in both the things inside the equation, where the z goes here and the z0 goes there. Once you plug them in, you have a very messy kind of looking equation, very long one. And then in this case, all you got to do is isolate for t. Okay, so how do you begin isolating? You send this km, you send this ks onto the right side with the kn t environment, and then you isolate for t from there. If you do isolate for t yourself, you'll find out it's going to be negative 1 over kn, because remember, there's the negative in front of it. Okay, don't forget that. That negative 1 over kn times all of that mumbo jumbo. Now, all you got to do is kind of like look at the patterns to kind of help you understand what's happening. So all I did is I took this negative and I inverted the signs of all of these guys, because once you absorb the negative n, or you multiply the whole equation by -1, all you're going to do is all the negatives will become positives and it'll switch it order. So in this case, you have now, instead of having kn plus kn plus kn times t environment minus t0, you have the other way. You have t0 minus t environment minus ks over kn and all of that stuff times exponential to the negative k and t. That's the first part of the equation. And minus, because all of these were negatives, so all you can do is just like multiply it by the minus. All you're going to get is this equation right here. Or actually, I just kind of saw an error here. Yes, so just might as well fix it right now. That shouldn't change anything that we did. So that should be a plus, because of when you're moving stuff around, you should be able to get a plus. And let's get back. A little typo here, should be plus, and that's the t steady state that you figured out in this part here. It's just about looking at things. If you don't see it, that's fine too, but yeah, that's the TSS. Now what they want you to do is they want you to make an equation. The name of the equation is going to be S of t, and the S of t is a special function defined as the t minus TSS. They define it this way. Okay, I know my t is this, and in that portion right here you have TSS. Okay, so if you move that over to the right side here, you're going to get t minus TS, which tells you that this portion of the equation is nothing but S of t. Okay, if you want to do it old school, you can plug this t here and then do the math. From that point onwards, you'll figure out your S of t is just going to be that equation here. And why do we need it? We need it for actually fitting the data that we're going to do in 1D. Okay, so we're going to use that fact. We're going to be able to fit a data into this equation, because what happens is when you're trying to fit an exponential data, you got to take log of both sides and make a linear relationship with log of those values. Well, the log of those values will only be working if you have nothing but an equation where two things are multiplied. You should not have any constants in that thing being added up. In this case, we had this plus, all of that as a constant. We got to get rid of it, so we define ST as an equation where we got rid of that thing, and now we're left with just this piece. We'll fit a model for that, and then we'll work our way back to the actual equation. Okay, so once that's out of the way, we got this S of t, and now we're going to jump up to the next part. Okay, so now in 1D, what they want you to do is to actually take the ln of this equation, and then from the data that's given out to you, calculate the corresponding S data from the given T data. And once you do that, all you got to do is plot a function inside Excel to fit that situation here, and then compare both of these data to get the values. Okay, so what I'm going to do is I'm going to start to like make a linear equation here. I'll explain up to this mark, and then we'll jump to the Excel part. Okay, I'll show you how to make a sheet, how do you get to these numbers, how they all work. I'll show you that. Okay, so now this is my S of t equation that we want. If you take a ln of both sides, what you're going to do is you take a ln of this side, you're going to get ln S of t, and ln of all of this can be figured out by taking ln of two things that are being multiplied. So when you do that, all you're going to get is ln of the first thing plus ln of e to the power negative k and t. And that thing all together is just negative kn times t. So now here you have a linear relationship where ln of st is your considered y value. This is going to be your b value plus this is going to be your a value times t. So this is how you have a relationship, a linear relationship here. So now if you make a column in Excel with this y value and these x values, of course they're t, but yeah, in these x value, and then you do a linear fit for that data, you're supposed to get a line that's going to have this as its constant y-intercept, this as a slope. Okay, so now I'm going to explain you how to make it. Once we go in there and find those values, we're going to jump back here and then explain from that point onwards. What I'm going to do is I'm going to start to like show you how to make an Excel sheet for all the data that we have. So I'm going to try to copy stuff out of this. So let me copy the data that's given out to us. I apologize for my really weird mic, or actually the mouse. It's going to make a lot of noise. And also my keyboard's pretty noisy as well. So So yeah, we have the data. We got the start of the measuring, day 1 with no sun and day 1 with sun data. So remember the part that I talked about where you have to find the average value to find the best fit for the steady state data. So that could be very easily figured out. So the mean value could be easily figured out using the average formula in Excel. So all you got to do is put equals to, and it'll pop up this thing. You click on average, and then you got to select which data you need the average of. So looking for the data for 60 to 120 for no sun. So you do that, and you hit enter. It's going to give you this mean value. So that was the temperature that we got for the steady state value that we used in 1B. Okay, so same thing for, so I'm going to label that as no sun. And then one with sun, you can do the same thing. Let me just kind of move this here. So mean with sun, same thing. You just got to put an equals to, average, click on it, and then select the data that you want to take the average of. That's going to be for 60 to 120 minutes off the data with sun. So when you do so, hit enter, you get that as the average value. So you can use these two values to figure out whatever you needed in part 1B. That's where I got those values from. Okay, so now let's try to make a function here. In this case, we're trying to find a fit for ln of s of something values, right? So as s is defined as the capital T minus T steady state, let's figure out the T steady state first. So I'm gonna write this as TSS. T steady state is nothing but the steady state value for the no sun. So just a disclaimer, 1D specifically tells you to find the function that's going to fit very well for the no sun data. Okay, so we're only going to focus on no sun data, not for the ones. And then also, some people have doubts on this. The steady state value of a whole dynamic is always going to be one single value. Okay, so in this case, when we had day 1, no sun, all of this data has just one steady state value that we already calculated here. Okay, so I'm just going to copy that. Going to be equals to, putting that thing in there. Okay, so we got our TSS value. Now how do we calculate our S values? The S and all those T's are defined at whatever the temperature was at that time. That temperature is represented in this row, minus the steady state. So you click on those, and that's going to give you a result here. Okay, so these are the values. How do you copy the formula down? We need it up to 55 minutes. So I'm going to copy it down up to 55. Okay, that didn't work. Okay, hold on. Because the reason is, I'll tell you. Because when we use this formula here, it has to have these values copied over. So if you want to use the same steady state value but vary these data here, all you got to do is put a special formula here. You put a $sign in front of F and a $sign in front of 2. What that does is it fix the reference to just that cell for calculating TSS values. However, it will change the B2 values to B3 and so on when you copy it down. So when you hit enter and then you copy it down now, they should give you the new values of S of T. Okay, so we figured out the S of T values for respectively T values. Now all we gotta do is take a ln of this and fit the data. Okay, so ln, I'm gonna make another column. Ln of that data is, oopsie, no capital T. I'm gonna use a small t here. This is nothing but literally just ln bracket of whatever is in this data value. So you punch it down, that's the ln of 4.466, and if you want to copy down, you're going to get the corresponding ln values for all of these things. Okay, so now what we're trying to do is we're trying to make a linear fit. There are two ways to do it. Either you can do the long way, where you have to do the actual calculations for residual of squares and all that stuff, and then find the A and B value, or else you can use the feature in Excel to help you out. Okay, so I'm going to do the feature in Excel way. My solutions, however, will include both. Okay, the Excel file that I sent with this thing on the Google Drive will have both the least square method and the actual slope method done by Excel to kind of give you just extra proof that it works. Okay, so just for clarity, what I'm going to do is I'm going to try to choose, these are going to be my X values, right? These are the times I'm going to plot, and these are going to be my Y values, the ln of S of T. hold on, what happened there? Gotta undo that. Okay, so what I'm gonna do is I'm gonna start to like go here. I'm gonna insert, and then I'm gonna go. Actually, I want a scatter plot, so I'm gonna go here. I'm gonna choose a random scatter plot. Okay, it's just doing all kind of stuff. So I'm gonna do is I'm gonna select data. I'm gonna get rid of all of these things that I already put up there by itself. I don't need them. I'll just take up the values that I need. I'm gonna cancel them all out. So now my X values, I can click on this button and select where my X value is gonna be. And the data range, you can choose that to be this. Okay. Why is it not working? Okay, I think it needs, let's try another way. Okay, the way how I like to do it usually, I'll show you that. So I'm gonna delete that chart because I don't need it. I'll reattempt in making this chart. Okay, so what I do usually is I take these values and then move this like 1 over to the right side. So then I have an extra column here. What I'm gonna do is I'm gonna put my t values there. Nothing but the same stuff, just copied over here. So that I have a better way I can easily plot this thing. I'm gonna paste all of these. So once I have these t values, what I can do is I can select these both and then go to like insert and go to recommended charts. It has a lot of them here. But what we wanna have is scatter plot. Is it in the list? No. Okay, so we'll just go here. We'll choose our own scatter plot. And that's how it should look like. Okay, that's how the scatter plot looks like. For different t values on the x-axis, you're gonna have a different ln values here. So now it looks kind of ugly. Let me try to make it a bit nicer. So I'm gonna do is like change the chart type. Be very specific here, okay? You don't have to do this, but I'm just doing it here. Even if you go for the line chart, don't go for these solid lines. Go for the point ones, okay? Take this one, and you have this like a nice line here with the points, okay? Once you have it here, what we want to do is we want to find a linear fit, okay? So all you got to do is click on this chart, and then head up here. I don't need that. You got to head up here and add a chart element, okay? If it's not there for you, just go to the chart design heading here, and it'll show up. You go add chart element. You got to go trend lines, and you got to go linear fit. And this is how you get your linear fit. So how do you find the equation of that thing? You select the linear line that you got, you right click on it, you go to format trend line, and all of these things what you have is display equation on chart. Once you do so, and you're gonna get this value here. And that's gonna be the equation. So in this case, your slope is negative 0.3438 plus 1.9782. So this is what was funny usually when we try to work on this. That's what the value that you'll get, okay? But there's a very subtle case. So what I discovered here, if you fit the wrong chart, you're gonna get the wrong value here. That's the only catch with Excel, okay? So make sure, the reason why I put it over there, this answer is wrong right now. What I'm gonna do is, I'm gonna increase the size of this a bit, so. Okay. I can't do that, but whatever. So, gonna try to like click on this. You gotta change the chart type. You gotta make sure that you have a scatter plot, and then you choose this if you want to see the lines, or the dots are gonna be fine as well. If you choose that, it's a scatter plot. This is the actual value that you're looking for, because what you need here is the actual equation of the line. Before that, I was showing you a different line, because what Excel does is when you fit it in a different model and you're not choosing a scatter plot, it'll automatically populate some extra data in between these points, and it'll fill up those extra spots just to kind of make up a better like a looking graph. But that's going to be introducing false information in our analysis. We don't want that. So I'm going to just use this thing, and this is the equation. In this equation, what you got, I'm going to zoom in a bit. So this is my equation. In this case, your slope is negative 0.0688x, and then plus 1.6344 as your y-intercept. Okay, so we're going to keep that in mind, and then we're going to jump up back to the work and start to compare and solve for the values that we're looking for. But that's about it. that's how you get the values for the actual equation here by using the formula and the functions made in Excel. Okay, you don't have to include this chart. It's completely up to you how to do it. However, my Excel sheet that I send with the solutions will include both the ways. Okay, so let's get back to the actual. Okay, so we're back here now. In this equation, so from Excel, we got this data here. If you remember, we got the slope here to be negative 0.688. The actual value in decimals is somewhere more than that. And then the y-intercept is what we got here. So now this is what it's telling me the relationship between the data, which is ln of SOT, with the t is going to be. So once I know this relationship right here, and I compare it to this equation that I had here, in this case, whatever is going to be the slope of my line, which is the t value, in this case should represent whatever my kn is. So if negative kn is equals to negative 0.06876, it's just like by comparing the coefficients, you can say directly that kn is literally the slope of the line that you get. Okay, why? Because you saw that it already is here. Okay, so now given that value, what you can do is you can easily calculate kn. So now, how do you calculate the km? That's where the tough part is. So now whatever this whole thing is, so first of all, there are two approaches, and I'll tell you exactly which one to take. Okay, I spent a lot of time on this. I want to make sure everybody understands what I'm talking about here. So, but this line equation that you got, the y-intercept that you got, 1.6343, must be whatever the y-intercept here is, right? So one way to do so, just independently work on this problem, is to actually find out that this must be equals to that, taking exponentials of both sides, and moving all of this stuff onto the right. What you get is that this km over kn ratio, which you already figured out in part B, comes out to be something different than you figured out in the previous part. So by this data, the km over kn ratio is 4.3741, which gives you a resulting km value of this. Okay, and because of how the data is structured, you cannot find the ks value. However, this approach is not a good approach. I'll tell you exactly why. But before we do that, let me talk about another approach. So from here, you already figured out the kn value. From the previous part, you know km over kn is just that number that you figured out in part 1b. So using that ratio, you can figure out the km value to be that. That's 0.3464, which is different from 0.3007. Okay, so which one do you take? I try to actually go to the end of the problem and actually see which km value would fit our function the best. Okay, I'll show you once we are done with this, once we figured out the model. I'm going to show you how I actually fit up this data. And to my surprise, this km value works better to fit all the points that we have in the data than this one. So the choice here is completely up to you. I choose this one because they're close enough. You can't be too wrong with this. If they're close enough, they're kind of okay. But the reason why I chose this km value, which I figured out from the ratio from part 1b, is because it gives me better fit to the function. Okay, I'll show you on the graph exactly what I mean. Okay, so given that part, if you're using the ratios, that means you can go back and use the ratio to find ks as well. Okay, so it kind of makes sense because in the problem they're asking us for km and ks. Well, if you use the data to find the km value, there's no existing ks in that data because no ks exists here. Okay, but if you're looking to solve for the ks value, you have to use the ratios. And then it comes back again. If you have to use the ratios, why don't you just use the ratio for km values, right? Why do all of this work? And why can't you just jump up straight up to the km value from the ratio? Okay, so a lot of things supporting this. I spent more than a day thinking about this, what's happening here. But yeah, this is supposed to be the correct km and ks value. Not supposedly exactly correct, but more accurate km and ks values. Okay, then that's it. So once we have all of this information, we should be able to see a function that kind of fits very well into the model that we're talking about. Okay, so what I'm going to do is I'm going to show you that in a second, and we're going to discuss how that data fits over there. Let me get you to the Desmos Applets, the actual function that we figured out in Desmos, and see how better it fits. So what I did here is you can actually make a table in Desmos of all the data points that I had. So this represents the no sun data, and from all the way up to 120. Okay, I didn't miss any points. I'm not only labeling 0 to 55. I'm labeling all of them because whatever function we got should be a good fit for all the data that we're experiencing here. Okay, so once you put all these values down, you don't have to, because I'm just trying to show you, demonstrate what's happening. What you have to see is that the steady state, the value that we figured out for the function, that should be km over kn plus the t environment. That's when you don't have any ks. So this is no sun case. The steady state value must be this. So what I'm going to do is I'm going to put up these informations here. I have a lot of functions defined, actually variables defined here. The kn value here is what we got from our analysis, from the data fit. The t0 is the initial value where this data starts at. So if you see, the very first value is 37.5 degrees. So I'm going to choose that as my beginning value. That's this. The km value is computed using the ratio that we figured out. So the ratio for km over kn was 0.50384, and whatever my kn values are multiplied, this is going to be my km value. That's what we chose, is 0.3464. The environment temperature is 28 degrees Celsius, so I'm going to use that as a variable here as well. Now, in this case, what you have to see as a define y equals to TSS, so this dashed line represents the steady state temperature, okay? And what we should be observing is all these points should be kind of close to the function, because the function should kind of fit this model the best possible way it can. So the function is given as this, so 0 to 120, because we're only talking about that data value. That's the initial minus the steady state, e to the power negative kn. And then if I go to the right side, you'll see plus TSS. So that's the simplified version in symbols for the function, but we're just doing the same function that we figured out in 1C. Nothing crazy here, same stuff. Once you plot that function, you see how close they fit, if it's that kind of not that hard. So I'm going to try to change this axis so you can see it better. How about we start at, let's say, 30, 31, yeah. And then we'll go all the way up to 38. So if you see that, of course, it's not going to be the perfect fit. It's going to be somewhat close to the data that you have. And then how do you define close? It should roughly have the same amount of data points below the function than above the function as well. So roughly the same kind of thing. But what I wanted to focus on is, if you remember the other km value that we figured out, if we change this one, okay, this was the original value from the ratio, but the data value that we got was 0. Instead of having 0.34644, we had 0.3007 that we figured out, and we ignored that value because that wasn't a good fit. Let me show you what I meant. So right now you see that picture here, that is for this, and then I'm going to plot another function. So I'm going to do is just go here, going to make a copy of this function. Once you have a copy, I'm going to label that as T1. This is a separate function. And now in this case, what I'm going to use is the TSS value. I'm going to change that to the steady state 1 value. Okay, I'm going to go there. And then I'm going to add a slider here. And that thing is nothing but the same value here with a different km. So all I'm going to do is I'm going to copy this thing, and I'm going to go here and paste it. You don't have to do this. I'm just showing you like what I meant. Hold up. Add a slider. Control V that here. So that's this. We're not going to use the same cam. We're going to use the other cam that we figured out. So I'm going to kind of like literally take this off. I'm going to plug in the value 0.3007. So this is what the other k value was going to be. And then I choose that one. I'm going to label this function with some other color. So let's call that like orange or something. Okay, so now you can see both the functions. The t function here is with the kn value from the ratio. The t1 function here is the function which we figured out the km value to be from the data. Okay, which one here is a better fit is very subjective, because you can see both of them does a good job. Okay, there's nothing crazy here. If you shut off one of them, this looks like a good fit as well. But if you shut off the other, that looks like a good fit as well. So it's completely up to you which one you choose. But from my recommendation, what I would say is you should write a single line explaining why you chose whichever km value you chose. It's just like a way of explaining what you did to have more confidence in your answer. But what I wanted to show is I wanted to show both the cases, and then trying to show you exactly what it means. In this case, if you have a steady state temperature of 3 point this, if you chose that value of km, the steady state temperature changes as well. Okay, so it's kind of directly relationship with the ratios. But yeah, you have both of them. So now you can feel free to write your answer in any way you like it. From me, both of them are valid. But from my personal perspective, I see the ratio is being a better fit, and it's completely up to you. You can choose them. You can choose both of them. You can say the km could be both the values depending upon how you see it. Both of them are a good fit, and if you want to like kind of justify your answer, I'm going to share a link to this one as well. You can like kind of take screenshots or whatever from this to kind of show them what you mean. But yeah, that's about it. Once you see, so this is how you fit a function for a data that's given to you in an exponential form, and it has a steady state constant value. Okay, so the technique is kind of okay, but I hopefully you guys know now how to fit this data in actual sense. Okay, and that's about it for part from 1D. All right, so coming back to the last part of this problem, there is a lot of words. What I'm going to try to do is just try to explain you what it means. So they said in the differential equation, Kn is a parameter that's being controlled by the surface area of an organism. So it's proportional to the radius squared because it's area. And then they said the metabolic heat production rate depends upon the volume of an organism. So it's dependent upon R cubed in this case. And they want you to figure out why is it preferable for you to be bigger in the environments where you're living, where temperature differences are way too much. So I'm going to consider like a case of Arctic region, because they kind of put it out there. So when you're in Arctic, what happens is the temperature of the organism's body is way, way, way more higher than the environment's temperature. Okay, so when you're given that context and you make this ddT equation, I'm assuming that Ks is 0, so not kind of like talking about the sunshine effect. Even if it doesn't matter. Sunshine effects is going to be the same for both of them. So what I want to focus on here is when you make this equation here, Km plus Kn to the power Kn times T, environment minus T. If that's true, then this is going to be less than 0, because T is going to be much bigger than T environment, hence you're going to get a negative answer here, which means your equation will somewhat become like this. So I'm going to factor out a negative to just make it very obvious for you to see. I'm going to substitute for the Km and the Kn values like we talked about here, and now my ddT becomes this equation here, where you have Km replaced by Kmo R cubed and Kn replaced by Kno R squared. And then I took a negative out, I flipped the signs in the between, so this one goes there, that one goes there, to just kind of make it look nicer. And now in this case, what you can see is if you factor out the R squared, this term represents the rate of generation of heat, okay, and this represents the rate at which this thing leaves, okay, the heat that's leaving your body. So given that thing, what you can see is if the rate of production is higher than the rate of consumption, the rate at which it leaves, then you're going to be able to heat up your body, okay. To be able to produce heat, you need your ddT to be positive, because you want to increase the temperature if you're in the Arctic region, right? So how would you do that in the quantification term? You need all of this to be greater than 0. Okay, so I put them here in this condition, which means that if this quantity is bigger, okay, in relevance to this, you will have more heat production. Okay, in this case, it's proportional to R, and even KMO is a constant that's proportional to the volume and the mass of an organism, as it said in the problem. So bigger size will result in bigger KMO times R value, which makes dd/dt a net positive quantity. Okay, so if your R is small enough, what happens is that the volume will be small as well, so KMO will be small, which results in decreasing temperature because then this term will be smaller than this term. If that happens, then you're going to start to lose your heat because then dt/dt will be negative. You don't want that because you're in the Arctic region. The animal wants to actually sustain the body temperature and stay in the comfortable zone. So you can answer this in the other way as well by saying if you are small in size, you'll have a decreasing temperature described by the dt/dt equation, which is not preferred. Okay, so that wraps up the first question. A little bit longer, but yeah, we're getting there. Let's talk about question 2. Okay, question 2 is now trying to talk about the subject of M. So metabolic rate of heat is given by M of T, and they've given you this equation. Okay, I'm gonna like kind of fast cut this through before I put you guys to sleep. So in this case, K1, K2 are constants, while T0 is the preferred temperature. Okay, so in this case, you have it here. That's the equation. We have that as your preferred temperature. Now, the first question I want you to do is figure out M prime of T and find the critical points. So when you do take the derivative of this, most of you guys already did it. You gotta take it with respect to T. Okay, I mean capital T. So when you do that, what you're gonna get is eventually just this function out here. And once you match up with that, you see there are no critical points for this function because K2b cannot be equals to 0. Exponential functions cannot be equals to 0 as well. So nothing in the numerator will be equal to 0, which means you're going to always have a decreasing behavior because of this inherent negative sign in front of it. So no critical points, and for all the values of t, this function will always be decreasing. As the denominator is always positive because it's squared at the bottom. And exponentials are always positive. B and k are also given condition positive as well. So always going to be having this inherent negative sign in front of it, which means M of t is always going to be decreasing. Okay, then the second part asks you to figure out where it's the steepest. Okay, and then you got to use the second derivative to justify your answer. So again, a lot of tedious math here, but I'm not going to walk you through this. It's just completely up to you how to do it. Use calculators, you refer to my work, completely up to you. So you'll be able to check the PDF and see what's happening here. You take a second derivative of this function, and you end up with this term here in the green box. And you see the only way this is ever going to be equals to 0, so this exponential is never going to be equals to 0, never going to be equals to 0. Only way you can make this equal to 0 is when you have this factor going to 0. And when you do so, you figure it out, you need your t to be equals to t0. Because when t equals to t0, this whole thing goes to 0, so e will go to 1, and 1 minus 1 is just going to be 0. Okay, you can take a ln and then solve it as well, but I'm just kind of like lazy and I figured it out by myself. So this is going to be the t value that you need for the inflection point. Okay, so at the inflection point, technically that is going to be the critical point of your slope. The critical point of your slope represents where it's going to be the steepest. It could be either downward or upward, doesn't matter for us because we're just considering the steepness. So you can just right away say the M of t will be most steep at this point because that is going to be technically the critical point of the slope function. Okay, and that's how you get this part. Now what they want you to do is observe the asymptotic behavior of this function for 2c part. And let's see. So when your temperature is very close to 0, what's going to happen down there in this equation is that when this is close to 0, this becomes e to the 0, which means you have this whole term just kind of like goes away. Okay, very small. It doesn't matter. You don't have it playing any role here. So when you see that, all you're going to be left with is just going to be k1 over k2 over 1, which is just k1 plus k2. Okay, so in other words, this is like an inverted Hill function, if you kind of remember that. The inverted Hill function has this kind of behavior like this, and this is the most possible value they can ever take, and that happens to be at t equals to 0. So in this case, the most possible value is k2, So we'll take that value when it's closer to 0, and because of this extra k1 hanging out there, the total value of the function will go to k1 plus k2 here. And now when t equals to infinity, what happens down there is that this term gets very big. Okay, when it gets very big, what happens is it's in the denominator, so this whole thing will go to 0, so only going to be left with the k1 value. Whereas in the actual inverted Hill function case, after some time this just becomes 0 at the end. So same analysis, you're going to get this value and that value. Now knowing this information, they want you to sketch this graph and then talk about how the parameters look like. So when you start to sketch this graph, on this axis you're going to have m of t, this axis you have t. So we know when the function is very close to these values, you're going to start up to have a k1 plus k2 kind of nature. So this is the value of k1 plus k2. So if you have that, it's going to start up at that point. And then we know at t0 is the most steepest. It's going to be decreasing throughout, but it's going to be most steepest here at this spot. And then you just draw the curve and you settle down to be k1, because that's the horizontal asymptote for the values of t that are very big. Okay, so you kind of get this like rough sketch of this, and you have to represent each one of those quantities. How do they affect what's happening? So in my discussion, what I said is if you have k1 just represents the vertical shift. So it's being shifted up by the k1 value. If you turn k1 down to 0, what happens is this whole thing will just shift down. Okay, so if k1 represents the steady state MT value after a long time has passed. Okay, so after the temperature is above the preferred temperature of an organism. So for all the values that are bigger than this value that the MT function will take is represented by k1. Okay, so if you increase the k1, you'll raise the overall MT, overall rate of production for this whole thing, for all the values of t, because it's just literally a vertical shift. Okay, increasing k2 values increases the heat production only for this portion here, because if you change the k2 value, this is going to shift up and down, just that portion here. And once you do that, all the values before this will go up or down depending upon how you turn the k2 value. So that's all you got to say. It's going to increase the heat value if you increase it for all the temperatures that are less than the preferred body temperature. Okay, B is a positive constant that controls how fast you switch. So this is a smooth switch. If you go faster, if you go even faster, the bigger the value of B, the more sharp is going to be the switching. Okay, the more steep it's going to be. And that's also kind of visible in the formula for the slope here. The slope depends upon B. So the bigger B, the more negative the slope is going to get. Okay, so B controls that part. And then what's going to happen after that, the favorite temperature marks the point at which the heat production is constant at a K1 value. Why is that so? Because once the organism has reached its preferred temperature, the metabolism just slows down and doesn't produce much heat because it doesn't need to heat up more than that. Okay, so that's where the spot kind of comes in. When you hit your favorite preferred temperature spot, your metabolism stops producing the extra heat that it needs to and settles down to whatever the constant K1 value needs to be at to maintain that temperature. Okay, and that was this part. Now 2E is kind of where most of the people will have doubts and stuff. So we're trying to talk about an equation for humans. So they're using the same analogy before that they did, but now that Km is going to be replaced by the m of t function that they gave you here. And they want you to figure out steady states of that function for different values of environment. Okay, so in different environmental temperatures, how does a person's body behave, and what is going to be the actual steady state temperature that they're going to reach in all of these bodies? You got to figure that out. So we're going to use Newton's method for this. Now to apply Newton's method, they've given you a bunch of constant values. When you compose the function like this, when you plug in all of those values, K1, K2, B, and the Kn values and T0 value, you get this function right here. So this is what I'm going to be solving for the zeros of. Remember, Newton's method is only there to help you solve for the zeros of a function. Okay, so given that fact that you only need that, this is going to be my function. This function has two unknowns, which is t environment and t. What we're going to do is we're going to treat the capital T as the variable and the t environment as a parameter that we can vary to see how t behaves. Okay, So for this one, what I got to do is figure out the f of t. That's just the function itself that we figured out in the top part. And then the derivative. Why the derivative? Because remember the Newton's method formula is just the next value. It's just the x minus 1 plus f of x of n minus 1. Oh my god, I just went outside. But yeah, you get the idea, because to apply the Newton's method, I need to see the formula, because then it's easy for me to type it in an Excel sheet to make it. Okay, so we're going to start to make an Excel sheet here. The graph is going to be talked over there. So this is just a summary of what I'm going to talk about in the Excel sheet, and I'm going to tell you how to make this graph as well. So let's go there and I'll show you how to make this sheet as well. Get to the Excel sheet. I'm going to just use the same sheet. So the reason why I'm doing that, because I want you guys to be able to see, I'm going to use this extra sheet down there to kind of do the analysis. So because we need to start to like make our data for the t environment values going from 0 to 45. So I'm going to just try to put in the t environment values. For this one needs to be starting at 0 going up to 1. So when you do that, select these two and then drag down up to 45. So you're going to get all these values here. So these are the different t environment values we're going to use. And what I want to find is this column here needs to be the steady state value. Okay, so how do you figure out the steady state value? This is what we're looking for. And this is going to be computed using Newton's method here. Okay, so what I'm going to do is I'm going to start to like show you exactly what I did here and which formulas I used. We're going to be applying Newton's method here. So we need to make 3 columns first. I'm going to start to like talk about it. This is going to be my f of x. This is going to be my f prime of x. And then the last one is going to be my initial guess. Okay, the initial guess is going to generate my first values here, and then the steady state is just going to sit down there. And now that steady state will belong here, and then it will help me generate the other values that I'm looking for. Okay, so when you're at 0 degrees Celsius, you got to figure out the function, you got to figure out what's happening. So what I did is, it's very tedious. Okay, I want to make sure that you guys follow the same formula that I did for most of the time for all the values. Okay, so what I'm going to do is I'm going to show you exactly what I did on the sheet. It took me like a long while to kind of figure it out, but I'll show you. Let me just copy that over. And if I bring that here, the formula that I'm using here is going to be in raw form. Just hold up, why can't I copy that? Okay, copy that here. No, hold on. Okay, my brain's trying to freeze up here, but I'm gonna try to do it. Copy this formula. So you kind of see it already over there. And that's what it means, because it's referring to the other book that I'm talking about, but we have them side by side opened up. So what I'm going to do is I'm going to try to replicate the same thing here. I'm going to type it in front of you. And then let's go from there. So the formula that I had is going to be equals to, so we're inputting the first function here. If you remember on the document that I gave you, the actual function was there, and then I'm going to just use those values. So what I got to do is it's going to be 3 plus 20, because that's the value for that thing, divided by 1 plus exponential. That's how you write e here. Exponentials 3 times the, what do you have, w? 3 times the value of the column. So we gotta pick up the initial guess value. Okay, so I'm gonna try to put it out there. I'm not gonna use it here. Just hold on. Let me just put that up here first, because then I don't know where it go. But yeah, initial guess. So this is gonna be my initial guess value, where I'm gonna be starting my temperature at, and then my steady state will be calculated accordingly. So the function, my initial guess, because I did it from actually the graphing utility software to figure out what's happening. So I used Desmos to figure out what should be the good starting spot just for once, and all the other ones are just going to be the same stuff. Okay, so what I'm going to do is just use that one. 28.75 is a good spot to start when you're at this environment temperature. Okay, so the function value at that T environment and at that initial guess temperature, I'm going to figure that out. I'm just going to write it in. It's going to be 3 plus 20 divided by 1 plus exponential of 3 times the actual value that you chose here. That's going to be the initial guess value minus the ambient temperature in the equation that's given out to be 37, or actually the preferred temperature. In this case, T0 is preferred temperature. That's this value, exponential, and you just that's this portion, and all you need from this point onwards, you gotta add, or actually add 0.8 times the actual A2 value here, so the environment temperature, minus the value that you're trying to solve for. It's all gone, but I'm going to type it in, okay, because I know that's going to be an E2. So that's this, and if you hit enter, that's going to be the value of the function at that spot. So I'm going to make this a little bit bigger so I don't have to like work with those. So this is the value of the function, and you know it's very good guess because your function is already very close to 0. So this was a good guess for this. Nice. So now we got the function formula in. We got to find the derivative formula now. Derivative formula for that one, again, same stuff. All you got to do is just be very careful what you type. Okay, so I'm gonna go here. I'm gonna try to type here. So what's happening here? The derivative that you got is negative 60. Okay, times the exponential. That should be times. My bad. So exponentials of 3 times same this value minus the 37. That's the preferred value of an organism's body for humans. In this case, and then you gotta close all of this and divide it by oh, did I have an extra one there? Oh no. Can it go back? Can I go back? No, I can't go back. Okay. This is the hassle, because when you're typing it in 2 different sheets, it kind of just like messes it up, but I'm gonna attempt it again. Minus 60 exponential. Okay, I don't know why. Exponential of 3 times of the value that you have for the guess minus 37, and that closes this part, that closes the exponential, and that closes the numerator. So once they're closed, you gotta divide this by, at the bottom now you're gonna have 1 plus exponential of, same thing, so 3 times the guess value, so E2 minus the 37, the preferred temperature. That closes this guy, closes the exponential. The numerator is a whole square, so you gotta do that. Let's say you erase it as a square, and then you gotta take away 0.8 from it. Okay, and when you hit enter, that's what's supposed to be your derivative value. Okay, the tough part of the job is done. That's all what you needed. Okay, so now this is going to compute your steady state value. Okay, the steady state value by Newton's formula is the initial guess minus the function at the initial guess divided by the slope at the initial guess. So Newton's formula will spit out a steady state of 28.75 here. Okay, and that's pretty close because that was literally the initial guess. So we kind of knew that if this value matches up very close to be 0, then these and that initial guess were very close as well. So now how do you copy these formulas down there? What I'm going to do is I'm going to try to use that same value as the next guess here. And what you can do is you can just like move that value over there. I'm just going to literally call this value. And then I'm going to try to drag drop, calculate the function at that value, calculate the derivative at that value, and then you're going to get the actual value of the function here. And that's 29.75. So if your temperature in the environment goes up by 1 degree, your steady state value is going to be 1 degree above it. So it's kind of like a very linear relationship. That's okay. But if you copy it down here, now whatever was this value comes into my next guess value. So I'm going to evaluate my function here. I'm going to evaluate this guy, and then I'm going to evaluate the next steady state. And that's 30.74. And we're getting there. So now this thing is generating values for us. All we need is to feed it with enough stuff. So I'm going to copy all the way down here. It's going to be rubbish values, so don't worry about it, because just copy all of this down. And then I'm going to copy all of this down here as well. And all of this down as well. So a bunch of stuff happened. There's a lot of things here. This is how you have all the data generated here. Okay. So now what you see here is for every T environment that you have a preferred steady state temperature that you're going to achieve in that environment. Okay. All of this data here is just for the help. Okay. The reason why I have this f of x pointed up here, because if you see that, in this case, all I'm trying to check is if my steady state is close enough or not. And how do I figure that out? Because if my values of f of x are pretty close to 0 here, probably just 1 decimal, some of them are like off, but it's not crazy off. If it's close enough to 0, that means whatever value you got for the steady state is also kind of close enough to the actual steady state you're looking for. Because this is a numerical method and we're not running enough iterations of Newton's method, we're not going to be able to get the absolutely accurate results, but this just does the job. It's not too crazy here. What we don't focus on is the initial guess. So what I did is, once you have this first initial guess here, the second initial guess will become whatever the value is for the steady state of the previous one. So all of them, they go like this here, and 29 comes from here, and 30.74 comes from here. So technically, the initial guess for the next steady state temperature is literally the previous steady state temperature. And that has been working completely fine for me. So we figured out a lot of stuff. So now what the question is asking us is to give this data in 2 specific ways. So first of all, we need to graph this thing out. And we got a graph with the steady state with respect to the T of the environment. So very easy and standard way to graph it. All you got to do is just select these 2 things, go to insert, and you got to look at the recommended charts. And there you have it. Any of this charts is going to be working. So what I do is I usually just take this value, and yeah, that's a good enough function. You can kind of like do some modifications here to kind of make it look nice. I did it in mine as well. I'll show you exactly how to do it. So that's pretty much it, what you needed. However, I want to show you some things. So what they did is they wanted us to figure out the temperatures of the environment in which our steady state value needs to be in 36 degrees Celsius to 38 degrees Celsius, or in other words, the comfortable zone for a human body. So if you see here, until this spot, all the steady state values were below 36 degrees Celsius. And after 9, you hit the 36 one. And then all the way up here, you're still in the 38 range. So this is kind of the good zone. So I'm going to label that good. So this is like the nice zone. So if your environment is ranging from 9 to 35 degrees Celsius, your body is going to be comfortable because that's deemed as the comfortable steady state temperature for human body. Okay, but if you're above this, let's say in this zone, it's going to become a little bit cold. So I'm going to use the cold one here. look at the blue. So that's going to be uncomfortable in a cold sense. Anything above that zone here in the 36 is going to be like hot. So we have like 3 zones here. The comfortable zones here. So you got to give them this value from 9 to 35. So what you can do here is try to edit this chart to kind of make it look nice. So what I do here is you go here, you go to chart design, and then you got to have a lot of chart elements that you can edit. We got to use the axis titles. So you got to use both. You got to use primary horizontal. That title is going to be the environment temperature. So you can change that thing here to T environment. And then you got another one here for the primary vertical. And that's going to be your steady state temperature. I don't know why it's so weird sometimes when you're typing in Excel. So I'm just like using short names, but I'm just trying to tell you how you can make this graph yourself. So once that happens, what else we can do is we can add up a chart title. But before we do that, let me just try to make sure I have this. So format the plot area. If you do that, you can have like all sort of things here to kind of represent what's happening in the shape. What we can do here is you click on this axis and you say format axis. What you can do is you can change the data set value where you want to begin and where you want to go. So we can start at the axis value. So this is talking about the horizontal. And okay, so I don't need that, but yeah, that should be automatic because we don't need the horizontal one. We need to work on the other axis, the vertical one. So what I'm going to do is shut this one off and try to see. What I'm trying to do is like format the major grid line. No, I'm not going to do that either. Okay, format axis. Automatic. So if I do that, it's kind of weird. Okay, so my bad. I didn't see it. I'm blind. So you look at the bounds here. In this case, the minimum bound you want to set up because just to like see where your data is, it's good to just start at 20, 25. And then your maximum bound needs to just be wherever your data is eventually going to get. So it's close to 48, so 50 is good enough. So once you have it, you can have this data like kind of nicely represented here. And that's it. One fancy way how I did it for my graph, you'll see it. You can add labels, you can add all sort of things in this. You can make it look nicer. What I'm going to do is I'm going to show you how I did it in my Word. So I'm going to select data. What I'm going to do is I'm going to, instead of having one single series, I'm going to have 3 of them. So I'm going to take this one off. I'm going to choose my my data range in this zone. Okay, so this is going to be my data range here. When you plot it, so this is going to be my series 1, series 2. I don't know. Okay, so it's plotting those things. What I want to change that. This A value is not supposed to be plotted. Only this series is supposed to be plotted. I'm going to call that series. The horizontal data needs to be coming from this side. So once that's here, this is the series, and that's the part for where the temperatures are like this. So I want to make sure that I have the colors matching up. I go to Format Data Series, and then I go to this line option. I make sure this is like kind of blue, because I'm trying to make it this way. And what I'm going to do here is I'm going to select data. I'm going to add another series to it. So in that series, my Y values are going to come from these portions here. And then my horizontal labels are going to come from these values here. So once I plot it, this is the next series here. I'm going to add another one for the last hot data. So the hot data Y values are going to come from this side. Hot data X values are going to come from these ones. So when you press OK, okay, that doesn't look nice. Maybe what I need to do is, okay, let me just try to get there. Select data. I'm going to get rid of all of these series. I'm just like having fun here at this point. You can skip forward if you want. Just trying to make this look nicer. So horizontal axis labels. I'm gonna take all of this data just for the sake of it. So all the horizontal category is gonna come from these guys here. So how about I combine them? Then I get rid of this. So this should show me just my regular data. That's cool. So now I'm gonna add another one. For this case, the y values are gonna be just this value here. And I press OK. So that turns blue. That's good. I'm gonna add another series here. So if you add another one, you choose those y values to be the cold y values. The comfortable y values, you choose that and you hit enter. You're supposed to see that kind of graph here, but that should be shifted. I don't know why it's not shifted, but in my version it does. Somewhat, I'm just going to copy that from here. So I'll show you exactly what I did here, which you'll get in my sheet here when I send it. So if I paste that chart here, I'm just going to delete this one out of the way. Same stuff, same thing that I did. I don't know why it's not working this time. I'm just gonna delete this chart and move this one over there. So that's how I did it. In this case, what you can do is add those labels, made it look nice. The blue zone corresponds to the temperature where it's too cold. The green zone is the comfortable zone, and the red zone is where it's too hot. So I have all those labels over there. Just kind of makes it look nice. You can feel free to take the same data if it's okay with everybody in the OSH people. But yeah, try to get the same data. My sheet will include all of this. But now you know how to make an Excel sheet and kind of predict the data that you were looking for. We needed this graph. That's number one in part E. And then the last part is to give them the temperature range we're looking for. And that should be 9 to 35 degrees Celsius. Okay. And that's about it for question 2. Let's jump to the question 3 once I go back to the actual document. Okay, so we're back at it now. Now you kind of have an idea why this graph comes from and exactly how I figured out that it should be 9 degrees to 35 degrees Celsius. Okay, the sheets are going to be, so there's going to be one Excel file, which is going to have both the sheet 1 and sheet 2 for OSH1 and OSH question 2. Okay, so it's one Excel file, both of them. Download a copy to yourself and then start editing it in your way if you want to do it, but that's it. Question 3 is relatively quick, very easy to kind of understand what's happening here. So what we're trying to do in this case is using the Euler's method to figure out whether our estimate is too high or too low. Okay, so they were kind of like very nice about this. They didn't ask you to solve much of the stuff, but just kind of conclude things. But yeah, that's cool. So they've given us a dy by dx, okay, which we're going to call y prime, as 1 plus x squared over e to the power y. So it's an implicit equation here. And then you're supposed to find in the first part the second derivative of this function. So in order to do second derivative function, all you got to do is just use quotient rule to begin with. But because of implicit differentiation, wherever you see a y, the derivative of y must be y prime, and you got to multiply that in the situation there. Once you do it, y prime is nothing but this whole value. So you can substitute it back in there, like how I did it here. You can simplify the expression. You're going to get this whole thing in front of you. Okay. So once this is your second derivative, let's go back to the idea, why do you even need this thing? Okay. The reason why you need this is to estimate what's going to be happening to a certain function. What I'm trying to do is I'm trying to tell you what's happening. So let's say you have a function like this. This function concaves up. Okay, I'm drawing on top of things, but yeah, just trying to understand what happens. If you draw a tangent here, you try to approximate the value of the function. Whatever approximation you're going to get is going to be on this tangent. That's this value, but the actual value of the function is right here. So this gap right here, represented by the arrow, is the error in the approximation that you get. So in this case, the function was concaving up, which means the slope is growing much faster than you actually think it is. But tangent slope is fixed, right? So the actual slope of the function, the actual value of the function will be much higher than the fixed tangent slope. So you can develop the rule of thumb that when you have a concaving up function, right, and you draw a tangent approximation down there, it's always going to be too low. But if you have a concave down function and you draw a tangent on top of it, this tangent is going to be higher than the actual value of the function. So concaving down functions at some point are going to give you over approximations, and then concaving up I'm going to give you under approximations. So in this case, they've given us this point here, and we've figured out the double derivative. All we got to do is check the double derivative of this function at that point and see if it's concaving up or concaving down. So when you plug them in, what you get is negative 1 over e to the power 2a. Well, e to the power 2 is always going to be greater than 0, so this will always be less than 0 at this point. So in this case, what it means is that the function's second derivative is negative, so it's concaving down. And just like how we talked about, if function's concaving down and you draw a tangent here and you try to approximate values, you're going to get the values that are higher than the actual value down here. So this is how you can say the approximate will be a little bit too high. Very simple. So now we got to estimate in the C part, we got to estimate the slope. Okay, so we're trying to estimate this guy, and beforehand we're trying to estimate the y values. Now we're doing this. So in order to apply the Euler's method, we needed a derivative of the function. In this case, we need a second derivative because we're just evaluating the derivative itself. So now to judge in the previous case for y, we needed the second derivative of y. Now to judge in this case, you're judging y prime, you need the double derivative of y prime, which is just triple derivative of y. Okay, so you can be, because you already have the double derivative, what you can do is take the third derivative, find it out. That's one way to do it. Okay, all this algebra is completely up to you. And then you need to plug in the point 0 and a, because that's the point of interest we're looking at. Okay, at that point when you plug it in, you see this function is always going to be positive. Okay, and then when you see that this triple derivative at this point is always positive, which means that this function here is concaving up. So if you try to estimate certain thing on a concaving up function, you're gonna get a lower estimate. Okay, so that's one way to do it. The other way to kind of approach this problem is we've figured out that whatever approximation of the y values we're gonna get in 3b are gonna be too high, right? So let's say what you did is you approximated the values here. When you approximated the value of y in this case, you're going to call that y prime, like y on a sign on top. So I'm going to call it approx y, that if that works out. Yeah, so this is the approx y value. And we figured out the approximate value is a little bit too high than the actual y value. So when you're given this and you try to figure out the derivative at a little step ahead of it at the approximated y value, you're going to have that little step plugged in and the approximate y value here. However, if you try to find the actual derivative without the approximation, you're going to plug in this and the actual value of the function at 0 plus delta x. When you plug it in, you're going to get this function here. Okay, because the x values are the same in both of these cases, just the y is different here. Okay, in this case, you're going to call the y as the actual y, so I don't have an approximation sign there. In this case, you had an approximation y, so that's this one. Now, because this function, this approximate value of y is bigger than the actual value of y, and these guys are in the denominators, so this resulting in a bigger value will mean this is going to be smaller, okay, than this comparison. Because if you see closely, I'm going to repeat it again. We established that the approximate value we're going to get are going to be too high. Given that fact, and when you observe the dy by dx at the approximate y value and the actual y value, well, this e to the power y is going to be bigger. This guy is going to be bigger than this guy, which means this fraction itself is going to be smaller than this guy. So you can say the derivative at the approximate y value is going to be smaller than the derivative at the actual y value, because the approximate y value is higher than the actual y value, and the derivative is inversely proportional to the y value, because the bigger the y value, the smaller the derivative is. Okay, so there are two explanations in front of you. You can use either the third derivative approach and just kind of come up, oh, this function is concaving up, so it must be a lower estimate. Or you can just figure out, in this case, if you have an estimate of y prime here, approximate of y here, the derivative at the approximate value of y is going to be less than the derivative at the actual value of y. Both of them are valid ways to work through this. So now that wraps up everything. I have this little thing at the end just for checking myself. You don't have to focus on this. So it's just my work that I did to just check my answers. You don't have to see that. But this document with the PDF plus the Excel documents, the sheets that I made, and the more formal ones are going to be uploaded into the Google Drive. The link to that thing is in the description of the video. So feel free to go there, download a copy of this, then change your values, and then you can just ask me any questions that if you have. I'm open to discussions. This OSH was pretty long, a lot of tedious, a lot of stuff going back and forth. So if you got something different, I'm always open to discuss. Please feel free to contact me. You guys know how to reach out to me. And yeah, that's about it. Thanks for watching.